Okay, that's great. Thanks for that, Brendan. So this is session 3. I'm Kuhn Verbruggen. I'm with the Geological Survey, and myself and Anna Bitgood, based up at UCD, are co-chairs for this session. So our first talk is John Appa, and John is with the UCC Marine Geology Group. So John's going to talk about marine litter. So John, over to you.
Hello, everybody. I'm John Appa, and I'm presenting on marine litter accumulation in cold water coral habitats, a case study of 2 Irish special areas of conservation. So that's my team, Prof. Andy Fila, who is the leader, Luke O'Reilly, and Larissa Macedo. I wish to acknowledge Dr. Aaron Lim, who used to be with the group and made significant contribution to this work. So why study marine litter, and why is it important? And what at all is marine litter? Well, it's any persistent manufactured solid material that is disposed of in the marine environment. These solid material threaten the growth of marine organisms, including cold water corals. As a result, these cold water corals have become vulnerable and are protected under EU Habitats Directive, and some have been designated as special areas of conservation. These SACs are special management tools that are used to protect vulnerable benthic fauna and cold water corals in our case. So these are my study sites: the Porcupine Bank Canyon, which is the red ellipse, the Belgica Mount Province, which is the red rectangle. The Porcupine Bank Canyon, of course, is a submarine canyon. It's the largest canyon on the Irish margin, and it's farther away from land compared to the Belgica Mount Province, which is closer to land and shows both outcropped and buried mounts with trending channels. In terms of regional morphology, the Porcupine Bank Canyon can be divided into the canyon head, which shows a gentle slope and is sediment-dominated, the canyon flank, which is steep with exposed bedrock, and the south branch, which is actually a small canyon attached to the main canyon system. Current speeds of up to 31 centimeters per second has been recorded in this canyon. The Belgica Mount Province can be characterized into the downslope area, where you have large number of carbonate mounts which slightly intrude into the midslope area and which is also slightly sediment dominated. The upslope area is heavily sediment dominated, and you find current speeds of up to 41 centimeters per second in the northern area. How did we acquire our data? We used the Holland 1 ROV from the Marine Institute to collect videos of the seafloor. We characterize and quantify the litter based on how they are distributed and the proportion of these litter items. We also collected vessel monitoring system data, again from the Marine Institute, and we use these data to determine how many vessels are fishing while in these SACs. And based on this information, we determine whether these SACs are effective or not. And so these are examples of litter items that we identified in these SACs. You have a metal, you have plastics, you have fishing nets, and you have fishing line as well. What is interesting here is that you have benthic fauna interacting with these litter materials. And so it's not all that bad when it comes to marine litter. In terms of composition, we realize that you have large proportions of plastics and buoy in the Belgica Mount Province, whereas you have large proportions of fishing gear and plastics in the Porcupine Bank Canyon. And by fishing gear, I mean fishing line and fishing nets. In terms of litter distribution, 80% of fishing gear and 11% of plastics were mostly abundant in the PBC, whereas 55% of plastics and 14% buoy were commonly detected in the BMP. And so litter was more abundant in the downslope area in the BMP, whilst it was more abundant in the canyon head in the PBC. It is interesting because in the downslope area, you have large number of carbonate mounts which tend to trap these litter items. And so in this part of the province, litter material tend to concentrate. In terms of abundance, the composition of litter is different in both SACs. From the vessel monitoring data, we noted that more than 60% of vessels from more than 8 countries were engaged in fishing while within these SACs. And these fishing vessels were particularly engaged in bottom water, mid-water, and shallow water fishing, which is very worrying because these SACs are closed to fishing, and they were established particularly to protect these vulnerable cold water corals. And so in conclusion, I noted that regional morphology affects the distribution of litter items, that these SACs are being compromised, obviously because you have fishing activities going on there, and that different management strategies must be applied because you have different compositions of litter in these SACs. We also advocate for regular monitoring campaigns so that fishermen who are caught fishing in these SACs are meted out with harsher and stricter punishments, if possible, to deter other fishermen who would want to fish in these SACs. Thank you.
Thank you, John. That was pretty quick. Good stuff. There's questions coming in, but I just wanted to ask you first: the distribution of the litter is it being reworked based on its weight and the morphology of the canyons, or is that actually how it's been deposited, do you think?
Just based on how it has been deposited, and I mean we did that based on whether they are distributed in the canyon or distributed in this Belgica Mount province. And depending on the regional morphology, you could decide that, okay, they are abundant in the head or abundant in the south. So yes, both ways, yeah. I believe so, yeah.
Okay, there's a question in here from Aoife Braden, and she's wondering, is it better or worse to remove the litter, like the fishing gear, not the plastics, once they've been colonized or whatever? So once they've been colonized. So if it's there and it's kind of been absorbed into the substrate or whatever, are you better off leaving it, or is it more destructive to actually try to remove it? You might have got an idea of that from the ROV dives.
So it depends on the situation. These litter items generally have chemical effects on the environment, and so if it's easier to remove them, well, that is good and it's welcoming. But in the case where if you are removing them will affect or destroy other benthic organisms, then that is a challenge because we saw that you have some kind of interaction with these benthic fauna. So it's not all that bad. There are good sides to it. Yeah. Yeah.
Mm-hmm. Yeah. I don't know if Anna has any questions coming in on YouTube because she's watching YouTube.
We've got one question come in from YouTube so far, which asks, does litter tend to stay fixed over time? So have they tried to revisit any areas to see if there are any differences over time?
So this was just a one-off survey, but then it's possible that these litter travel, they drift with these currents that have been recorded down in this deep part of the ocean. So yes, it's possible that they can travel, but then this was just a one-off survey. And so at the moment, this is the location that we have identified these litter items.
Okay, and if I can come back, I know one of your recommendations was harsher penalties that'll go down well with the fishing community. But what is the current situation in terms of monitoring? I mean, the vessel, the VMS, I think it's called, Vessel Monitoring System, that's accessed by, like, the Naval Service have access to that and Parks and Wildlife. So in theory, isn't it the case that these SACs are being monitored and there is fishery patrols?
So I was in contact with the Marine Institutes, just as you said. They get this data from the naval part of the Army.
Yeah.
And so they only sit and receive this information, and then the users also go and then pick them. But I think the real job is being done by these naval people who go out there and then get this data.
Yeah. And the Naval Service, they have a really good GIS setup to monitor this, so I guess it's up to them to do it. Okay, thanks a million. That was really good. Thanks a million, John.
Thank you very
Anna,
much.
do you want to introduce the
Let
next
me
speaker?
stop my screen there.
Okay.
Yeah, so thanks very much, John. That was great. So I'm going to move us on to our next talk, and I hope that John's talk was enough to pull you out of your post-lunch lull. And if not, then we've got some more exciting talks coming up. So our next speaker is Efat Baboudi. And Efat is a PhD student with IGRM, and she's going to talk to us about variable stress state with depth in the shallow crust of the north of Hawke Bay in New Zealand. So Efat, I'd like to invite you to share your screen, please, and you can take it away and introduce yourself.
So how I should share this share content?
Yeah, you should be able to click the share content and choose the screen that you'd like to share.
How is it now?
That's great. Yeah, we can see that.
Okay. Good afternoon, everyone. Today I'm going to talk about how a stress state is changing in North of Hawke Bay in New Zealand. So how is the sound? Is okay, everything? Okay, and sorry. I'm going first talking about where is the Hawke Bay and then why we are studying a stress state in this area. Hawke Bay is located in the east coast of North Island in New Zealand. Is part of Hikurangi subduction margin. Hikurangi subduction margin is located in the east coast of North Island, where Pacific plate subducted under Australian plate. This subduction is happening in a oblique movement in direction of west-east and increasing from south about like 30-35 millimeters per year to 45 millimeters in the north. Across the Hikurangi subduction margin, there are different tectonic regimes here. Close to Hikurangi trough, there is a compressional stress regime, and moving to the forearc, there is a clockwise rotation of the forearc, and then there is some strike slip faults here. They are developed from south of North Island to north part of North Island, and then there are some back arc rifting in the center of North Island due to activity of Taupo volcanic zone. Hawke Bay or north of Hawke Bay are located in Hikurangi subduction margin or central Hikurangi subduction margin that it is a well-known places for frequent rupture earthquakes and slow slip events that are happening here. Till now, there wasn't any comprehensive study of present-day stress in this area, and to assess the hazard risks in these active seismically regions, it is important to find out how a stress state from like a stress tensor like magnitude and orientation is changing. There have been some studies on focal mechanism from earthquake data, but they are located in subducting plate. And at the end, we are going to compare our results with the focal mechanism data and to find out what is the source of present-day stress in this area. To find how a present-day or in situ stress state is changing in this area, we are going to use borehole borehole data such as Weber image logs. The concept is that when we are drilling a well, we are removing material inside the well. So the shape of the well can be affected by the far field stress. Sometimes stress inside the wellbore, it can be exceed the stress far field stress, and so some parts of the wellbore fall out, and we have some failures. We call them borehole breakout. This borehole breakout, they appear as a broad dark zone, and with a 180 degree apart from each other. They can be useful in determining maximum horizontal stress and also orientation and magnitude. These borehole breakouts, they are happening perpendicular to maximum horizontal stress and in direction of minimum horizontal stress. So we use this, we try to gather the image log data and then interpret this borehole breakout to find the stress, maximum horizontal stress orientation in this area. As you can see in this picture, we plot the borehole breakout azimuth as a function of depth. You can see that borehole breakout azimuth, they are mostly directed in direction of northwest, southeast, and that give the idea of that maximum horizontal stress in direction of northeast, southwest. These results, they show that they are really in a good agreement to each other in different wellbores, and also show that the stress orientation with depth, they are completely consistent, and there are some small scale deviation like this area. They might be due to activity of faults or fractures in the area that, like, due to drilling fluid have been leaked to these fractures, so they activated them, but they haven't affected the overall maximum horizontal stress in this area. Then the other part of present or in situ stress is that having stress magnitudes. Stress magnitude, there are three components: maximum principal stress, least principal stress, and overburden stress. Overburden stress, as you know, is can be calculated from density logs and is integration of density. But Likov test for or Likov least principal stress. To estimate this stress, we use Likov test point data that have been reported during drilling. So what is Likov test or Likov pressure? Likov pressure is kind of pressuring test that they are we conducted some like a few meters below casing show, and then try to pressurize the formation. When we are pressurized the formation, pressure be increased over time as a linear function of the volume that we are pumping inside the wellbore. Then suddenly, when this mud weight it is starting leaking to formation or initiating a fracture, then pressure will be deviated from the linear trend. This point that the pressure will be deviated from the linear trend is Likov pressure or Likov point. And it is a good proxy of minimum or least principal stress in normal or strike slip regimes. Sometimes we have FIT. FIT is kind of Likov test, but it is the difference that they didn't continue the test, so we never reached the pressure that initiate the fracture. So they could be a good representative as like a lower band of minimum principal stress. We used this minimum principal stress from Likov test for pressure data from mud weight and overburden stress that estimated from density logs. As you can see in this area, pore pressure is really high. In some wellbore, it's really close to overburden. And even the minimum principal stress from FIT, that be lower band of minimum principal stress. So this plots, they show that we have mostly at least strike slip to compression or reverse thrust faulting regimes in this area, but some such as Chiara 2 and Chiara 5. In shallow part, like less than 600, minimum principal stress is less than overburden. Based on Anderson, they give that we should have a normal faulting regime in this area, but it looks like that this normal environment, they are really local and it depends on location to location. It could be due to gravitational collapsing or the other parameters, but they are localized and it's not general trend of stress maybe in this environment. So in the other part, we try to find out how it was interesting to see how our stress from a borehole, from shallow sediments, is changing related to a long-term relative plate motion or from the other stress indicators such as focal mechanism. Focal mechanism is a method that are using earthquake data to find that stress orientation, maximum stress orientation, and relative stress magnitudes. But in this area, most focal mechanism or earthquake data, as you can see, they're located at least more than 30 kilometers. They are located in subducting plate than overriding plate. But even they are in different plate. They show that there is a really good, they are in a really good agreement to each other. It probably could reflect that far field stress or boundary forces are controlling present day stress in this environment. The other part was to see how is this present day stress related to structure in this environment. As you can see here, there is a base map of top of Chiara limestone, and you can see that the environment is really compressional or I don't know, reverse fault or thrust faulting regimes. They are striking to north, east, southwest that give the idea that maximum horizontal it should be in northwest, southeast. So we see, as you can see here is a seismic profile based on depth for Chiara 2. We have shallow normal fault. They could be really related to collapsing, but mostly we have reverse fault or thrust faulting. They might be rooted to subduction interface. Subduction interface here is about 12 kilometers from the surface. But what is the, we were looking at what is the difference, why this is happening, like direction from a structure is different from present day stress that we are observing here. We come across that maybe be a combination of results such as high pore pressure in this environment, such as low coupling behavior in this area. First, about pore pressure. We try to estimate pore pressure. To have a pore pressure, it's better use some like modular dynamic test, DLSM test when you are drilling. But in this area, unfortunately, we have like for 3 wells for the whole Hikurangi subduction margins, the direct measurement of formation pressure. But we can use mud weight as a good proxy of formation pressure if we don't have a significant mud loss or kickoff. So we use mud weight in this area and then calibrated and corrected with DLSM test and repeat formation test for well bores that they have data. As you can see, there's an obvious difference between pore pressure in the north and in the southern Hikurangi subduction margin. And in some points, like this was, the pore pressure is really close about to like overburden stress. Bergen and Darby dating, they suggest that this high fluid pressure could be related to this equilibrium compaction or porosity reduction due to high convergence of or subduction of Hukrangi Plateau under New Zealand. Then the other observation is that coupling behavior in the subduction interface is changing from north to south. In the north of Hukrangi subduction margin, most they are experiencing slow, frequent and shallow slow sleep events and steadily creeping behavior, while in the moving to the south they are cooped together and there is no creeping behavior observed here. So we came to the conclusion that it might be these reverse falls are not active anymore. But if they are not active anymore, why we can see from stress magnitude the dominant stress regime at least be strike asleep to like truss faulting or compressional. So we think that yes, there is the compressional stress regime here, but due to uncoupling behavior on the subduction interface, the plate boundary forces like this is the forces that help to moving or subducting Pacific plate under New Zealand or Australian plate. They can transfer to the upper plate, and then due to probably if these faults are rooted to the subduction interface and due to high pore pressure, they could make a slip in direction of northeast southwest. So we think stress regime is compressional, but currently there is a strong component of strike asleep in direction of northeast southwest in this area. So in summary, what we saw was that breakout there in the northwest southeast that give the maximum horizontal stress orientation of northeast southwest. This analysis of like stress magnitudes give that the stress regime is more like normal strike asleep in shallow part, really like less than 500, 600, and then dominantly strike asleep to reverse faulting regime with depth. And this contemporary stress state, it is in good agreement with focal mechanism data, but it is in contrast with structural regime that we are seeing here. This contradiction could be related, mostly we think that related to coupling behavior that and pore pressure, and they are now imposing a northeast southwest sleep on the truss or reverse faults in here. So that's all, and thank you for listening. And at the end, I will be thanks for IGRM and SFI, GSI, and New Zealand Department for providing the data.
Great, thanks so much for that, Efa. It's great to see how we can actually measure the stress regime of these regions. There are no questions coming through on YouTube just yet, but if you have any, please do pop them in the chat. I think we have some questions coming in through the team. So
I have a question. Yeah, just looking at the shallow data first, rather than the big picture, deep data. Are the shallow boreholes, do they actually have implications then, practical implications for building development or piling development? Because if you've got those kind of high pressures relatively close to the surface, I presume they're probably geotechnical boreholes, are they? So is this something that needs to be taken account of in construction?
It could be. That's the plan. That's like it's important for New Zealand, especially in this region that they are really seismically active, to have a risk assessment plan to find how these faults are active or they are reactivated or they can be reactivated due to this high pore pressure. But we should in the future investigate that how much pore pressure needed to reactivate these faults or make the changes in this environment. And there are shallow, but like even they are about like 3 kilometers, less than 3 kilometers, and they can be also useful in resource development such as CO2 storage in this area. They've been used in the past for oil and gas industry, but it wasn't that much economic. But now maybe be useful for the assessment to see if be able to do CO2 storage in this area or not.
Yeah, would CCS not be a concern if the area is that seismically active that to ensure you have sealed reservoirs if you've got a repeated seismicity?
The reservoir, like the most formation are mudstone, but as you can see, yeah, they are highly fractured in this area.
Yeah, so you have the permeability. Okay, great talk. Thanks, man.
Welcome.
So if there's no questions come through on YouTube, but I would say thank you very much, Efat, for your talk, and I'll pass you back to Koen to introduce the next speaker.
Okay, thanks, Anna. So we're staying in New Zealand now, at least virtually. So the next talk is also it's dealing with emplacement and internal deformation. Whoops. Yeah, no problem. So the next speaker is Ben Cooven, and Ben can introduce his group. I recognize Aggie's name there as one of the supervisors. So he's going to talk about emplacement and internal deformation of submarine landslides constrained by resistivity image log interpretation. Ben, over to you. You can share your slides, hopefully, using the little share. Okay, no worries. The share content box there.
Yeah, thank you for your introduction. Thank you, Anna. And also thank you to Efat and John for their interesting presentation. I hope you can all see my slides now. Yes?
Yeah, that's great.
Yeah.
Okay, so hello everybody. My name is Ben Couvin, and today I'm going to talk to you a bit about my research. And my research for my PhD is about submarine landslides, and especially I'm going to talk to you today about how we can constrain the emplacement and the internal deformation of submarine landslides using resistivity image logs. So before we go into resistivity image log, I want to give you a little bit of background and how it came to that. So the first question of my project was to ask what is the lithological and rheological properties of slow-moving submarine landslides? How can we define them and define their movement specifically? Because we know of slow-moving landslides on land, but submarine slow-moving landslides or submarine creeps are not so well understood. So we would like to try and constrain their sliding mechanisms using seismic, core, and well data. And I've already used a first case study in offshore New Zealand with the 20 landslide complex using seismic and core data to map the extent and the morphology of these landslides in 3D. So I've discovered that the two units of the landslides, which were previously thought to be deposited in a similar way and emplaced in the same two large valleys, actually were very different, and a subsequent amount of time was passed between the emplacement of the two different units, the lower landslide unit and the upper landslide unit. And as you can see on this map of the base of the two units, the unit 3 was more deposited in the same way as a channel levee system or a deep basin fan, and you can see the feeder channel on the northwest, whereas on the left you have the base of unit 2, which resembles more what we can see on bathymetry data. And so I proposed a model for the temporality of the emplacement of these two different units, and said that maybe the sediment evacuation was downslope was the cause of the start of the deformation in both instances, but we can see that the deformation for Unit 3 and Unit 2 was actually very different, and they were emplaced in different ways. So now my question is, how exactly is this deformation occurring within the sediment, and how does it keep moving, really? How is the deposit deformed? How does it keep moving? And so to answer this question, we wonder how we can see the deformation internally. And since cores provide only limited 1D information, we use logging while drilling data, and specifically resistivity image data, to have more detailed images of structures. EFAT has already shown you how we can find the orientation of stress regimes, of stress states, using these very resistivity images, using the interpretation of breakouts on this data. But what I was more interested in was the identification of structures like surfaces. So I looked for bedding surfaces, fractures, and since what we're looking at is actually the unwrapped 360 degrees view of the borehole walls, actually what we are seeing is planes appearing as sine waves. So we are going to look for the sine waves, and this way we can interpret them as bedding planes or fractures or faults, depending on their morphology and resistivity fascies. And then we can trace the evolution of bedding angle and bedding strike, and also fracture strike and fracture dip angle from the bottom of the hole to the top. And so that's very interesting to find out patterns and how the deformation is evolving from one sedimentary unit to another. And so in order to make comparison of all these deformation processes, I didn't only look at the 20 landslide complex, but also at 3 other sites throughout the world where we had this sort of data. And so there is another site in offshore New Zealand, but also a site offshore Japan, and a site on a passive margin, this time in the Gulf of Mexico. And so I'm going to go through all of these results, but I'm going to focus more on one and then not really detailing so much the 3 others. But as I go through, I will kind of make assumptions of what we can infer from the results. So the Nankai Trough is the site offshore Japan, and it's a really interesting one, as we have a site, a drill hole through a sedimentary sequence that goes through a thick Mtd deposit that is overlain by a mix of hemipelagites and volcanic ash layers and thinner Mtd units, and is underlain by an undisturbed sedimentary sequence, Unit 1B. And what you can see here on this seismic section is that Mtd6 actually erodes Unit 1B as it is emplaced, and it forms a ramp here that the Mtd is going over. And you can see how Mtd was moved on the seafloor, how it was emplaced, and so the transport direction was actually from the north towards the south, and it will be important for later. And so at site CO18A, I look at the resistivity data that I had, and I could interpret the orientation of the bedding plane from the deep peaks I made and put them into stereo nets. And so what we can see, interestingly, is that we can look at the evolution of the bedding strike, the bedding direction, and the bedding deep direction and deep angle from the bottom to the top of the well. So we see that the bedding strike does not really change a lot, actually, from 330 meters down the well to the top of the well. However, there is a switch in the dip direction from dip direction towards the southwest, and then progressively it changes and goes towards the east, northeast and the east. But generally, there's not a lot of striking difference between the MTD units and the undisturbed units. However, when you look at the fractures, it's a different story, because the MTDs here in purple and in yellow, gold, have different orientations completely from the undisturbed unit, in which actually we didn't find a lot of fractures, and it was difficult to find a really strong pattern. But what we can see already is that the MTD6 presents like a strong east-west strike, very clear, with a dip towards the north, and it's a different orientation that we see for both the other MTD units, but also for the undisturbed unit, unit 1B. And what is also interesting is that the fractures orientate preferentially towards where it came from the scarp actually, and the dip direction is towards the north. And so it's a parallel to the direction of transport, and that might be interesting to see whether the strike being parallel to the slope of the MTD unit might have something to do with its formation. In Ruatoria, it's a bit of a different story here. We have a debris avalanche and then a debris flow that was produced by its deposition. And then we have site U1520, which is at the very toe of the debris flow deposit. And here we see a difference between the bedding strike in the undisturbed unit in green and the bedding strike in the MTD unit here in orange. And what's interesting is that here the bedding strike in the undisturbed unit is parallel to the coastline, whereas in the MTD units, it's perpendicular to the direction of transport of the MTD. Again, it's dipping to the north, and that's probably because we are at the toe of the debris flow, and that if the debris flow has stopped because of a rise in topography, it's expected that the dip direction would go to the north. When it comes to the fractures, it's very much the same story as the bedding. Actually, it's interesting that the fractures really have the same orientation as the bedding, although the dip angle is in the same direction, but with a stronger dip angle. But fractures have various orientation in the undisturbed unit. And so it's interesting to see that, again, there is a difference between the fractures in the MTD units and in the undisturbed units. And so we can probably infer from that there is the fact that the MTD has different fractures means probably the rock properties have an influence on the formation on the fractures and their orientation somehow. In the 20 landslide complex, we also have data, but it was of less, a much poorer quality, especially in the 40 top meters. And it was really difficult to interpret any structures in Unit 2. We have some fractures interpreted, but not a lot, unfortunately. And so here the bedding, again, it's not very varying from the bottom to the top. There's some variation, but they're slight. However, in the fractures, there are differences between each unit, which probably means that they have the properties of the material in Unit 3 and Unit 2, or the method of emplacements might have an effect on the orientation of the fractures rather than the stress regimes only. It's also interesting to point out that I can see in the data of Unit 3 here, a fracture clusters 10 meters above the base of Unit 3. Actually, at the base of the landslide unit here, we don't see a lot of deformation, and it looks like the deformation only starts to occur 10 meters above the base, which actually concurs with observations of colleagues in the US, where they see a weak layer, a layer of weak shear strength in this particular level, 10 meters above the base. And in the Gulf of Mexico, we have also Mtds that are actually very similar to those of the 20 landslide complex, but here we are on the passive margin. And what we observe is that actually, again, the bedding doesn't really tell us much except maybe a slight rotation of the strike here in the MTD unit. However, in the fractures, we didn't find any confirmed, like confident fractures that we could interpret in MTD2. And that's interesting because we were expected to find more fractures in MTD2, but we didn't find any. And so that might mean that there is actually the fact that there are on a passive margin might make the difference here. And so I only have preliminary conclusions on this subject so far, but what we can say is that actually resistivity images can be used to study the internal structures of MTDs. We can learn a lot from resistivity images, and we can see the evolution of the orientation of these surfaces from bottom to top using this method, and that MTDs here in all the cases actually show fracture orientations that are very distinct from those of undisturbed units, and that suggests actually that maybe the emplacement of the unit, the method of emplacement, or the rock properties themselves of the MTD could play a more important role in the fracturation style than does the surrounding stress state regime. And when it comes to MTDs at passive margin, they do not show as much fracturation as their counterpart on active margin. And so maybe the fact that these MTDs are on active margin could maybe have a role in the formation of these fractures, but that's not confirmed. And actually, I'm really open to your suggestions on how to best analyze these results. And otherwise, we keep looking into it, and with further analysis, we may constrain a bit more the emplacement and deformation history of these MTDs. I hope this was an enjoyable talk, and I'm open to your questions. If you have questions later, you can contact me at this email address or on Twitter at geo_benko. And you can listen to my podcast, IGRM, the podcast on Irish geoscience, on Spotify, Apple Podcast, and you can also follow us on Twitter. Thank you very much for your attention, and if you have any questions, please do ask them.
Thank you, Ben. Thanks for that. Getting feedback there, but there's a question in on Teams. Great to see from me for Braden. Great to see such a unique oriented data set. Are there any issues with scaling? And can you scale up the resistivity or core studies to the overall fan? And is it a linear relationship?
Sorry, scaling on. Can you repeat the question, please?
So with the data that you have, are there issues with scaling it up? Can you scale up the resistivity core studies you have for those point data to the overall fan? Is it? Can you expect a linear relationship in behaviors?
Well, yes and no. Actually, the cores, the sites, sorry, were chosen specifically to be representative already. So we would expect that it could, yes, scale up. But of course, it's also always easier to do it on several sites to increase the assurance of the results. But I think since there are IODP sites, IODP drilling sites, there is always a lot of time is taken to choose these sites, and so we believe that they are representative of the whole area.
Okay, and you mentioned that they're IODP sites, so I just wanted to check. So is the data that you're looking at from Hikarangi, is that from the IODP crews that Aggie and Dave both took part in?
Yeah.
Okay, well, that's good to see because GSI sponsored the participation. So I'll send you a logo you can include in the presentation.
All right.
Anyway, no problem. Anna, are there questions on YouTube?
Yeah, we've got a question coming from Connor. He says, thanks, Ben. And what do you think is the relative influence of gravitational versus tectonic forcing on MTD deformation?
Right. Okay. So most of these MTDs are actually close to the subsurface, and so at all this point, at least those of which I know, the stress regimes, for example, non-chi, we have actually more an effect of gravitation rather than tectonics, because the breakouts, the stress regimes is actually extensional, and so the influence of gravitation is stronger than tectonics, and the influence of tectonics is expected to be more at greater depths, actually.
Great, thanks. I actually have a question myself as well. You mentioned they had this weak layer towards the base of the flows, but not at the very base. Is this something that's kind of rheologically controlled? Can you correlate this with the lithologies down the holes?
So the lithology is pretty consistent, actually. There is not a lot of change from this part of the core to under there. Actually, when you look at the core, you can't really see a lot of difference in lithology between the two units. Mm-hmm. It's very consistent. So there is some sand at this interval, and so just below the sand, you have this so-called weak layer. But there is nothing we can see in core that is really really obvious that it's a weak material.
Okay, thanks. We have another question from John Gallagher. It's the same question. What is the maximum depth at which your model would be valid?
I don't know, actually. What is the maximum depth? I'm not sure how to answer this question, actually.
Okay, well, maybe you and John can chat afterwards. Yeah. Okay, that's great. Are we happy to move on to the next slide, Ben? Have you got any more?
Back to you, Anna. That's great. Thank you, Ben. Very good.
Thank you very much, Ben. Our next speaker today is our last one of the session, and it is Adrian Sux. Adrian's a PhD student at Trinity, and she's going to talk to us today about the replacement of calcite by rare earth carbonates and the formation of bastnasite. So I can see your screen there if you want to go full screen and then take it away.
Yes, thank you, Anna, for the introduction. So in the next 10 minutes or so, I would like to talk about how bastnasite can form in nature and our latest research result. But where to start? So rare earth elements are 15 elements corresponding to lanthanides. And these elements are fundamental raw material for our everyday life. So the screen you are looking at this presentation, or your phone or your headphones or any batteries, it surely contain rare earth elements. So they are just generally there, and especially in alternative energy technologies, so renewable energy technologies, there's a lot of rare earths required. So there's a general huge demand existing for these rare earth elements. But if we are thinking about the perspective of how many of the countries joining now to net zero, which is amazing, but there's like even further pressure on finding more rare earth elements and the demand for them. And especially now, I would like to highlight China, because they also pledged carbon neutrality by 2060. But the interesting part here that China is exporting over 60% of our rare earth element source. So if they're trying to become green, they probably gonna export less. So there's a huge urge on the market to find even more rare earth elements and find alternative sources. But where is rare earth elements coming from at this moment? So in these images, you can see bastnasite, monazite, and xenotime, and this is the three main source of our rare earth elements currently. So they are actually more abundant than many of our platinum group minerals. So the problem here is the extraction, finding a deposit which has generally economically enough, like high concentration enough rare earth elements to economically worth the extraction. So the problem we are facing here, that even if we have the mineral sources, it's generally difficult to separate the rare earth element from this mineral. So if we try to look for alternative resources like recycling our electric waste, it's often just more complicated and it could have a greater environmental harm than actual mining. So if we want to effectively raise our effectiveness on mining these rare earth elements, there's two other problems. One of them is that we are lack of understanding the biogeochemical cycle that describe the movement of rare earth elements. And the another one is that we also lacking information of understanding the main geological processes by these minerals, by which minerals containing the rare earth elements and other critical metals are formed and concentrated. So with simply saying, we need to understand more of the crystallization mechanisms and pathway of rare earth carbonates if we want to get a better way and more rare earth elements to maintain our daily life and have a really green future. So what we did is, instead of working natural samples, we synthesized rare earth carbonates, especially focused on basnasite in our experiment. And we used lanthanum, neodymium, and dysprosium, and it was a heterogeneous nucleation. And what you can see in this image, that we had the rare earth bearing solution individually, so like lanthanum bearing solution, neodymium bearing solution, and dysprosium bearing solution. And we put the calcite in this reactor. And then with these reactors, we placed them at different temperature, and we followed the reaction for days to weeks to months. So the interaction process, what we could see is that you have the rare earth bearing solution, you add the calcite and place them in the reactors. And then what happens here is that the calcite start to dissolve calcium and carbonate ions into the solution, especially close to the calcite surface. So what happens here is that the rare earth ions going to interact with the carbonate ions, and they nucleate on the surface of the calcite crystal, forming a new phase. And what you see in this image, this is lanthanum, lanthanite. And with time, as it's passing, it slowly eats up the entire crystal and covering it up. So the crystallization goes from outside to inside of the calcite grain. And we followed this interaction on with XRD as well. So what you see here is day 0. So this is just pure calcite. And like day 1 and day 2, and then after 11 days later, you see that how calcite is fully replaced calcite. So calcite is being replaced by new phases. So following these reactions at different temperatures, we ended up seeing this crystallization pathway moving from calcite all the way via lanthanite, calcite, all the way to basnasite, the last soluble phase. And what you see here on in picture A and B as lanthanum lanthanite, and on C you see neodymium lanthanite. And the interesting part here is that both of them were taken at ambient temperature, but this one is after 42 days, and this one is after neodymium is after 145 days. So there's roughly 100 days different between the two images. And but you see that lanthanite is almost, lanthanum lanthanite is fully like covered, so lanthanum lanthanite fully covered the calcite grain. Meanwhile, neodymium is just started the reaction, and we can explain that because of the ionic ruddy of the element itself. So neodymium has a smaller ionic ruddy, meanwhile than lanthanum. So that means that smaller ionic ruddy means that it has higher ionic potential. And then if an element has higher ionic potential, it generally leads to the fact that it's going to need more energy to remove the hydration shell of the ions. So it's either need like higher temperature to overcome the kinetic barrier, or it needs more time. So what you see here is that it's generally neodymium system need more time to go through the crystallization and start the nucleation. And this photo, you see the next phase is calcite. So this one is lanthanite system, this one is neodymium, and this one is the dysprosium system. And you can see an epitaxial overgrowth on the surface of the calcite. So this orientational overgrowth is not happening in dysprosium system. Again, because of dysprosium has actually the smallest ionic radii out of these three elements. So it means it has higher ionic potential. And this results in the fact that it takes more time to start the nucleation. And this time is generally enough for the calcite grain to dissolve more calcium and carbonate ions, especially close to the surface of the calcite crystals. So the supersaturation level is going to be higher. So by the time dysprosium is ready to nucleate, that it's going to be a really rapid growth, which result in general orientational defects, and it's not going to form an orientational overgrowth on an epitaxy on the crystalline on the calcite grain. And our final stage was observed as basnasite. So on A, you see lanthanum basnasite, and B, you see neodymium basnasite. And in this image, you see just simple how the crystals looks under a microscope, but there's no dysprosium basnasite here. And the reason for that, it's again can be explained because of its ionic radii. It generally have, like I said, the smallest ionic radii out of these three elements. And with this size of ionic radii, it's just generally not capable of forming basnasite structure. So dysprosium basnasite is just generally doesn't exist. So to summarize this mess what I was trying to talk about is just this one figure. So this is the final conclusion of the whole experiment we were doing. So you can see the elements we work with and the general observation of the crystallization pathway. So it's moving from calcite via lanthanite and cosite all the way towards basnasite. But here I mentioned that like the ionic potential can be overcome with raising the temperature. And you can actually see it here, that if you put lanthanite on ambient temperature, it's going to form after a couple of days. Lanthanum on ambient temperature is going to form lanthanite after a couple of days. But if you raise the temperature, it's actually going to be faster, and it's only need a couple of days to form cosite. But if you put it on 220 Celsius, after simple 1 day, lanthanum is going to turn into lanthanum hydroxyl basnasite. So temperature has, again, an important role in this overall system. And you can also see that there's no dysprosium basnasite here, as I mentioned, because of the ionic radii. And to finalize, that is a little bit of takeaway message from this old experiment. So the data was especially relevant because now we have a better understanding of what's happening in natural system, natural carbonate deposits when it comes to basnasite. From previous research, we know basnasite can form directly from solution, but now we also know that it can form via replacement of calcite. And we know now that it can follow a very complex crystallization pathway, which is mostly driven by the ionic radii of the rare earth element presented in the system and driven by the temperature. And I would like to thank you for your attention with this lovely image of a calcite eaten up by cosite dysprosium, dysprosium cosite. Yeah, thank you very much.
Thank you so much for that, Adrienne. There's some amazing images in there, really, really cool to look at. So just to start off then, it's a question from me, is how do you think this kind of understanding of the natural processes, so how the basnasite forms, is this something that could be integrated into the way we kind of process the rare earths when we're talking about how they're difficult to separate? So how can we kind of integrate this into like our understanding of how we would go about extracting and processing the rare earth elements?
Yeah, that's a really great question. So I was just having this discussion that I actually don't exactly know how we extract rare earth elements from basnasite, because any company who is doing that, it's generally a secret. So I don't know in details what's happening in there. So, but generally speaking, if you know how in natural ore system this crystallization pathways happens, you actually have a better understanding. So you might have a chance to actually know what to look for or where to look for this carbonate minerals. And then you're also going to understand like why it has a high concentration of rare earth elements, and it might give another view what else minerals we can use to extract rare earth elements. So yeah, that would be it.
Great, thanks. We have a question from John Gallagher, and he wants to know, does this mean that bastnäsite does not necessarily form in a single stage? And if so, this has very important implications for the understanding of carbonatite complexes.
Yeah, so that's actually a really great question. So bastnäsite can form in a single stage, but like as I was showing in this little figure here, so for example, in lanthanum system, if we place them on 50 Celsius, first it's going to form lantanite, and then it's going to slowly transform into cosite, and then eventually it's going to turn into bastnäsite. But the difference here is the time. So to follow up this reaction, it can go from days to weeks to months. So because of COVID, we were lucky enough to forget an experiment in one of the oven at 95 Celsius, and with lanthanum and neodymium. And from cosite, after like 4 months, bastnäsite was present in neodymium. Bastnäsite was present after 4 months, but still not fully transformed from cosite to bastnäsite. So you can actually get a peak between the stages, how they slowly transform from one stage to the other stage. Yeah.
Very cool. Do we have any questions coming in from teams?
Just a quick question: are there implications from your work in sort of exploration for bastnäsite, and given the importance of exploration for REEs, like if there's changes in our understanding of the formation, can that actually reflect in how we might explore for it, or how we might construct exploration for it?
Sorry, can you repeat it? I wasn't sure if I...
Are there implications in actual how we might explore for rare earths based on your work?
Yeah, so that's a really interesting question generally, because now we understand the crystallization pathway. So you more or less, if you have like bastnäsite in natural system, and until now everyone was focusing on the natural bastnäsite, and then we weren't really sure how rare earth elements ended up there. So what was the circumstances, how these minerals and deposits formed. So now with knowing like what was the origin of these minerals, you have a better understanding where you can look for these minerals in nature and exploration. But for extraction, like I said, it's generally needed more time and more time of mind to figure it out.
More research.
Yeah.
Good stuff. Great. Really, really important talk. Great stuff.
Yeah.
Yes, I think that's all the questions coming through. And that was our last talk. So thank you very much, Adrian, for that. That was great. And I'll pass you back to Brendan maybe now.
Looks like we've got ahead of time, Brendan, here. There you go. Another first for IGRM.
Yes, indeed it does look like we are a little bit ahead of time, but no harm at all. I did build a little bit of extra time into the schedule just in case of technical difficulties, and I absolutely don't think that it's bad news that we didn't have any technical difficulties. So that's okay. So that means we have a little bit longer before our next session now, so you have a chance to relax a little bit more. We'll be starting again for the final session at 3:30. So you have a little over 45 minutes to prepare for that. So I just want to thank our two chairs for this session, Koen and Anna. Did a great job. Thanks very much to all the speakers, and thanks to everyone who was watching on Teams and YouTube. And I'll see you at 3:30 for the final session. Thanks very much, everyone.